Hello everyone, welcome to another live session. Today we are going to discuss the chapter Nuclei from 12th Physics. As you know, it's a very small chapter with some portions deleted already, and we know so the rest of the concepts we are going to concentrate. Some questions from based on the weightage, we are going to do some questions from different topics. You can see the topics of the chapter, starting with profile of the nucleus. In the sense, we are going to make a nuclear profile, how big the nucleus is, and what is the mass of the nucleus, how heavy the nucleus is, what is the density of the nucleus. We discussed all these things right in the beginning of the chapter. That is what coming under the profile of the nucleus. Then followed by mass defect and binding energy, the hot topic of today's discussion. Then binding energy per nucleon graph, nuclear force, and potential energy of nucleons graph. We are talking about two important graphs in this chapter. One is binding energy per nucleon graph, binding energy versus mass number. Another one, potential energy of nucleons versus internucleon distance graph. Okay. And followed by radioactivity. As you know, I changed the color of that topic because that is a deleted one. But if you go through the past papers, we can see radioactivity was one of the very important concepts in this chapter. That is what I told you right in the beginning. That topic is deleted. So we'll concentrate on the rest of the topics. At the end, we have to go for nuclear reactions. Since radioactivity is deleted, I was just analyzing the past papers, and as I have shown you in the last discussion, this chapter also, I selected the number of questions asked from different topics in past papers, and it was radioactivity leading. As you can see, 33%. And radioactivity, we had so many subtopics like alpha decay, beta decay, gamma decay, nuclear reactor also included. So, but that portion is now deleted. So we have to go through only the rest of the topics in which we have mass defect and binding energy has maximum weightage as per the analysis. That's what I told you. That is a hot topic for today's discussion. And almost all concepts we have to discuss in this chapter is some way or other related to mass defect, binding energy, stability of the nucleus and all, right? Okay, so this is the way. And if you go through that, the listed topics are having almost the same weightage, average of 17 or 15 like that, So they are equally important. So we'll be doing some questions from all these concepts. Okay, I hope you're ready. We'll start straight with the questions. Question number 1. Yes, nuclear profiling. I told you from the profile of the nucleus. We'll start with the questions. Radius of a nucleus is nuclear radius. We were trying to understand how big the nucleus is, right? Yeah. Then in that discussion, we found radius of a nucleus R is proportional to a raised to 1 by 3. Actually, we know radius is equal to R0 a raised to 1 by 3, where R0 is a constant, right, which is 1.2 FM Fermi meter, 1.2 into 10 raised to minus 15 meters. That is called 1 femtometer, which is called Fermi. 1.2 FM Fermi is that value of R0. Okay, so it was proportional to a raised to 1 by 3, and we have a direct option here, directly proportional to the cube root of its mass number. A is the mass number of the nucleus. We know it is the mass number, total number of nucleons in that particular nucleus. So radius is proportional to a raised to 1 by 3, cube root of mass number. And that was a great start. Option C, yes, most of you answered. Option C is the correct answer, right? And remember this derivation also. See, we R is equal to R0 a raised to 1 by 3, that equation derivation is also important. We considered volume of the nucleus is proportional to mass number. That was the concept behind, right? Mass number, volume. If you want to accommodate more and more nucleons, see, total number of nucleons is called mass number, no? So if you want to accommodate more and more nucleons, it should be big enough. So volume will be increasing, or volume is proportional to mass number. And volume, assuming this nucleus as a perfect sphere, 4 by 3 pi r cube, is proportional to mass number A. Correct? 4 by 3 pi is another constant. R cube is proportional to A, or R is proportional to A raised to 1 by 3. That is how we got that relation. And the proportionality constant also we discussed. Okay, so for the question number 1, it was option C. Radius of nucleus is directly proportional to cube root of its mass number. Good. Moving on to the next question. Yeah. You're given mass number of 2 nuclei. Helium is 4 and that of sulfur is 32. Mass numbers is given. The radius of sulfur nucleus is larger than that of helium. Yes, we know mass number, helium it is 4. That means inside the nucleus of helium we have how many nucleons? 4 nucleons. That's the mass number. And for sulfur it is 32. So nucleus of sulfur should be big enough to accommodate 32 nucleons in it. Definitely it is bigger than that of the helium. That was the concept, right? Yes. And you're asked to find the ratio basically. How big the sulfur nucleus comparing to the helium nucleus. Yes, we can go to the same ratio. What happens? I'm not getting any answers for this one. Come on. Yes. Radius ratio is given. Radius of helium is given, proportional to mass number of helium whole raised to 1 by 3, correct? And radius of sulfur is proportional to mass number of sulfur whole raised to 1 by 3. Just taking this ratio, you will get the correct answer, right? So radius of helium divided by radius of sulfur is equal to mass number of helium, which is 4, divided by 32, the whole raised to 1 by 3, right? 4 raised to 1 by 3 divided by 32 raised to 1 by 3. So we can take 4 by 32 whole raised to 1 by 3. Yes, so we get 1 by 8 the whole raised to 1 by 3. And we know cube root of 8 is 2, right? So radius of helium divided by radius of sulfur is going to be just 1 by 2. Cube root of 1 is 1 and that of 8 is 2. So 1 by 2. What will be radius of the sulfur atom? The question is how much big, bigger this sulfur nucleus than helium. So radius of the sulfur nucleus you can find out from this. Rs is equal to 2 times radius of helium nucleus. So the fraction was 2, right? This is the correct answer. And that was option C. Yeah. Okay, you should not spend this much time to get your answer for these kind of questions, okay? Just taking the ratio of mass number. Now I am getting the answers. Yes. So option C, 2 times. Radius of sulfur is 2 times bigger than radius of the helium atom. Okay, so radius ratio, whenever you are asked to find radius ratio, there will be mass number relation given in the question. So just go for R directly proportional to A raised to 1 by 3. Nuclear profiling, I told you, we are going to make the profile of the nucleus. We understood how big the nucleus is from this relation. Okay, yes. Then moving on to the next one, question number 3. Yeah, I don't want to comment on this one. It's exactly the same. If R1 and R2 are the radii of atomic nuclei of mass numbers 64 and 125 respectively, then the ratio R1 by R2. I want to get answers now onwards. Yes, for this question. R1 by R2 you are asked to find. You are given the mass number ratio directly. We can go for R1 by R2 is equal to A1 by A2 the whole raised to 1 by 3. Yes. Yeah, be careful, like option C and D confusing. Yes, yeah. Yes, I'm getting so many answers there. So A1 by A2 is going to be 64 by 125 the whole raised to 1 by 2. 1 by 3, we know it is 4 by 5, right? 4 by 5 is the correct answer, D. Yes, so R1 by R2 ratio is going to be A1 by A2 whole raised to 1 by 3. Exactly the same concept is repeated in this question also. Now, question number 4. We have done with the size of the nucleus, right? So whenever we have like questions based on size of the nucleus, that part like R, radius of the nucleus, is proportional to cube root of mass number, right? That is very important. Now for this one, Next one, we are coming to the atomic mass unit. Atomic mass unit be used to measure the mass of an atom, mass of the nucleus basically, mass of the nucleons basically. Yes. So we are coming to the second detail of the nucleus, like in the profile, how heavy the nucleus is. Okay, for that we use it 1 AMU. 1 AMU stands for 1 atomic mass unit. Yes, I am getting correct answers from many of you. Be careful with the power. All of them are 1.66 and that is a correct numerical value, but only powers are different, so don't be confused. And most of the time these constants will be given in the beginning of the question paper, so you can just refer, go through that, don't commit mistake for a given answer. Okay, 1.66 into 10 raised to minus 27 kilogram is the answer for the question, 1 atomic mass unit. All right, 1.66 into 10 raised to minus 27. Okay, what is this 10 raised to minus 31? Have you seen this power somewhere? 10 raised to minus 31. What is a power 10 raised to minus 31? Somewhere we used it. All these powers are like that only. These powers we are familiar with. Forget the numerical values. Powers. Yes, exactly. Yes, Anas. Yeah. Who is this? Fake flip-flop. There is real flip-flop and fake flip-flop also. Mass of electron. Yes, yeah. Exactly, ME. Some of you told me like ME also, mass of electron. It was 9.1 into 10 raised to minus 31 kilogram, right? Mass of electron. There we used the power minus 31. And what about minus 19? Somewhere we used this. Charge of electron, right? 1.6 into 10 raised to minus 19 coulomb, right? And what about minus 34? Somewhere we used this also, minus 34. C was easy. That is why I answered that question. What about D? 10 raised to minus 34. Yes, exactly. Planck's constant. Yeah, Planck's constant, H. Right? We know 6.6 into 10 raised to minus 34 joule second. That was the Planck's constant. So all these powers are familiar with. So don't be confused. Okay, and what was 1 atomic mass unit? That also we required for the upcoming questions. 1 atomic mass unit, 1 U or 1 AMU is average mass of 1 nucleon, right? Mass of 1 nucleon. What do you mean by a nucleon? A nucleon can be either a proton or a neutron, because protons and neutrons are there inside the nucleus and they together called nucleons. So average mass of 1 nucleon is 1 atomic mass unit, because we defined 1 atomic mass unit as mass of carbon 12 isotope, right? Carbon 12 isotope divided by 12, in which this 12 stands for the mass number of carbon. Mass number of carbon is nothing but number of nucleons. Number of nucleons is 12. Mass of total nucleons divided by 12. Right? Mass of 12 nucleons divided by 12 will give you average mass of 1 nucleon. So we can say mass of proton, mass of neutron are approximately equal to 1 atomic mass unit. Not exactly equal. We know neutron is slightly heavier than proton. Right? Yes. But they are almost equal. Small difference between the masses. Fine. So that was 1 atomic mass unit related concepts. Coming to the next one. Question number 5. Density of a nucleus is related to mass number to the power of. Yeah, density. Nuclear density. Nuclear density. Yes, this was a very important concept and very interesting concept also, because yes, Jade. Exactly, correct answer. Yeah. Yes, yeah, many questions, many options are coming up. I can't read properly. Right. Nuclear density, we know it is independent of mass number. Mass number has no role in deciding density of the nucleus. Almost all nuclei have the same constant density. That is what we found, right? So, since it is free from mass number, a to the power 0 should be opted. That is the correct answer. Correct? Yes. Nuclear density is independent of mass. Independent of mass number. Yes. And here this proof also, another important derivation, just 2 marks question we get, show that nuclear density is independent of mass number. Nucleus density of a nucleus is independent of mass number of the nucleus, right? Okay. And that was the interesting thing, like density of the nucleus was huge. It's a lot. Size of the nucleus is negligibly small. We found the range of size of the nucleus is in the order of 10 raised to minus 15 meters. Femtometer, right? Because R0 was the constant R0 was 1.2 into 10 raised to minus 15 meters. That's the range of the size. Size of the nucleus is this much. 10 raised to minus 15 is very small. And mass we measured, atomic mass unit. Mass is in the order 10 raised to minus 27 kilogram, atomic mass unit. Yes, so negligibly small size wise and negligibly light mass wise, but density is a lot. And also that density is independent of mass number. For almost all the nuclei, density is going to be a constant. Yes, independent of mass number. Fine. So we found out density of the nucleus as mass by volume, right? Mass by volume. Mass of one nucleus is equal to mass number into one atomic mass unit. Mass number is total number of nucleons. One atomic mass unit is average mass of one nucleon. That will be total mass of the nucleus divided by volume is going to be 4 by 3 pi r cube. R cube is the radius. So A into one atomic mass unit divided by 4 by 3 pi into r cube is r0 a raised to 1 by 3 the whole cube. That is for the expression for radius we found in the beginning. Yes. Then a raised to 1 by 3 and 3 will be cube and cube root will be cancelling. A gets cancelled. So that density part will be free from mass number. Okay. So this proof is also important. So answer for question number 5 is option A. Right. Let's see. We are coming to that binding energy part. Now, binding energy of the nucleus EB is related to the mass defect delta M. Mass defect. Delta M stands for mass defect. How mass defect is related to binding energy of a nucleus? Yes, Allah. Yes, Rishma, Jade, Azim, Dhruvil. Yeah, I'm getting so many answers. So this is correct only. We know the relation. Binding energy is equal to delta M C square, right? Einstein's mass energy equivalence. Einstein's equation of mass energy equivalence. Del MC square. This delta M is called the mass defect, and the option B is the correct answer. Delta M C square. But we calculated binding energy using another equation, right? In the numerical questions, we get questions from that part also. We know if delta M, if the mass defect delta M is given in atomic mass unit, what did we do? We found this binding energy of the nucleus as that delta M, which is measured in atomic mass unit, is multiplied with 931 MeV, right? That is how we calculated binding energy. So the theory behind binding energy, the source to find out what exactly is the binding energy, we used this relation. We found some mass is missing. That was called the mass defect or missing mass, right? Mass defect. When a nucleus is formed, mass of the nucleus, actual mass of the nucleus is found to be less than the total mass of the nucleons. Right, some mass is missing inside the nucleus. That was mass defect given by delta M. Okay, delta M and binding energy are related in this way. That missing mass is converted to energy using Einstein's mass energy equivalence is equal to mc square. We found binding energy. But we calculated numerically binding energy in an easier way, like multiplying delta M with 931 MeV, because 931 MeV is energy equivalent of one atomic mass unit. If you convert one atomic mass unit into energy, you will get 931 MeV, not joules, mega electron volt. That is MeV, we know that. Okay, so delta M in atomic mass unit into 931. Fine. Question number 6, option B is the correct answer. Moving on to the next. Yeah, question number 7. You are given mass of a lithium nucleus is 0.042 atomic mass unit. That U stands for atomic mass unit. Less than the sum of the mass of all its nucleons. Binding energy per nucleon of this nucleus is nearly. So we have to find binding energy of the nucleons, I mean that particular nucleus, and we have to find out that value using this delta M. I just told you before in the previous question, if you know missing mass in or mass defect in atomic mass unit, we have an easier way of finding out that binding energy, right? So we know binding energy can be calculated as delta M into energy equivalent of one atomic mass unit, 931 MeV. So you can multiply 0.042 with what? 0.042 into 931. Why 931? We know if delta M, mass defect, is given in atomic mass unit, you can just simply multiply with 931. Your binding energy will be obtained in MeV. That will be the unit. Yes, I am not going straight to the questions because I was waiting for you to get the final answers. I expected that options. Yes. Izzuddin, Azim, Reshma, you didn't finish your calculations. You're half the way only. Whoever got that option D, I am getting so many option Ds. Whoever got answer as option D, make sure you completed your calculation. That is why they have given the option D in the question. You are asked to find, yes, I am getting more and more Ds. Look at this. You are asked to calculate binding energy per nucleon. Binding energy per nucleon is to be calculated, not the total binding energy. So if you multiply these two, you will get 39.1, yes, MeV. So when we do this, we'll go back to the options and you are given option D as 39.1 MeV, but you have to calculate binding energy per nucleon. That is your final answer. What do you mean by binding energy per nucleon? Binding energy per nucleon, which is Be bar, is equal to total binding energy of the nucleus divided by mass number, correct? Yes. So this is not your final answer. This is only binding energy. Then how will you calculate binding energy per nucleon? Binding energy per nucleon is equal to that 39.1 MeV should be divided by mass number of lithium. See? That should be your final answer. Yes. Now we are all coming back to option C, right? You got your mistake? Yes. So don't be in a hurry. Just cross check your result. They will give options like this to confuse you. And we will take advantage of that and we'll be ending up with a wrong result. Okay. So option C will be the correct answer now. Okay. Binding energy per nucleon. Binding energy per nucleon we calculated as total binding energy by mass number. Okay. Yes. So that was question number 7. Let us move on to the next. Yeah. Binding energies of atoms of elements A and B are Ea and Eb respectively. 3 atoms of elements B fuse to give 1 atom of element A. This fusion process is accompanied by release of energy E. Then Ea, Eb and E are related to each other as follows. You are given 4 options again as usual. You have to identify the relation connecting Ea, Eb and E, where Ea is the binding energy of nucleus A, Eb is binding energy of nucleus B, and E is the energy released during a fusion process here. Yes, we will come to that fusion process and all in detail towards the end of the discussion. Here in between, we get a question directly related to that energy release and binding energy. So let us go through that. I will explain that in detail. Energy release during this kind of nuclear reactions. We just need that particular concept to solve this question. More nuclear fusion, fission reactions are coming towards the end of this discussion to calculate energy release, binding energy change and all. Remember, for all these kind of questions, you have to remember if energy is released in this process, whether it is fusion, fusing 2 nuclei together to a bigger one, or dividing one heavy nucleus into 2, that is called fission. In those processes, energy released is always gain in binding energy, right? gain in binding energy. Binding energy gain. Whenever binding energy is gained because of some nuclear reaction, that excess energy will be released. That's what happens. Okay. Yes, and in this question, see, there will be some gain in binding energy because of that process, and that energy will be released. Look at this question. 3 atoms of element B. 3 atoms of element B. Okay, so we can say it is like 3 B atoms. Okay, fuse to give 1 atom of element A. See, it gives you 1 atom of element A. This is the fusion process happened. 3 B atoms fuse together to form 1 big A atom. Okay, we know that is called the fusion. We are fusing smaller elements, like, to get bigger nuclei. Now, binding energy of B is given. It is EB. So we can say 3EB is the binding energy before, right? Yes, before fusing. And now, what is the binding energy final? We got, as a result of the fusion process, the product produced here is atom A, element A. So its binding energy is EA. EA. We know energy released is always gain in binding energy. That is what I told you to remember. If there is an energy release in a process, in a nuclear reaction, it is because of the gain in binding energy. How can you calculate gain in binding energy in this case? Gain in binding energy is binding energy final minus binding energy initial. We can say EA minus 3EB, right? Yes. That is the binding energy change, final to final minus initial. That is going to be what? E. Correct? That is going to be E. E is the energy released in this process. Energy released is always, what did I tell you? Energy released is always gain in binding energy. Question says energy released is E. So what will be that energy release? Released energy will be equal to gain in binding energy. What is gain in binding energy? Final binding energy minus initial binding energy. What is final binding energy? EA. Because we got A, nucleus A, as a result of the fusion. What is initial binding energy? What did we do? How did we get A? By fusing 3 B atoms. So 3 EB. Correct? Yeah. Now I got answers here. So we will be just rearranging this, cross check the options. We are given different combinations. So in first 3 of them, it is 3EB is on the RHS. So if I take 3EB on the RHS, what will be the LHS value? EA minus E. EA minus E. So EA minus E is equal to E is one of the given option, which is C. Okay. So whenever you get question from energy release part from a nuclear reaction, we are getting more options, more examples later. So the basic thing you have to remember, if there is an energy release, it is because of gain in binding energy. For binding energy final minus binding energy initial. That will be the energy released during that process, whether it is fission or fusion. Okay, we'll come to that in detail later. Okay. Yeah, fine. Question number 9. A question based on binding energy. I told you again, binding energy and mass defect. That was a hot topic of the chapter. So we will focus on this concept more number of questions I added from this part only. So let Mn and Mp be the masses of neutron and proton respectively. Yes. M1 and M2 are the masses of neon, 10, 20. 20 is the mass number, 10 is the atomic number, and calcium, 20 atomic number, 40 is the mass number. 2 nuclei are given. Then you are asked to find the exact relation. M1 is neon. So it is given like Ne 10, 20. And M2 is given as calcium, right? 20 and 40. Then which option could be correct? Yeah, we did similar 2 questions already. Give me the answers. Which can be correct? Yes, we know when we form a nucleus. Yeah, yes, flip-flop, whoever it may be. You're getting the correct answer, I hope. Yes. Yes, Izzuddin, Hafiz. Yes, correct, exactly, correct answer. Izzuddin, cross check once again. You may be having more options, just cross check them. Options given as M2 less than 2M1, M2 greater than 2M2, M2 greater than 2M1, C, M1 less than some 10 times Mn plus Mp. Mn and Mp are mass of neutron and proton, right? You are given mass of the nucleons, Mn mass of neutron, Mp mass of proton, and both B and C are correct. So which option is going to be correct? Let us cross check one by one. See here, M2, you can make a calcium atom by taking, calcium nucleum by taking 40 nucleons. 40 nucleons. So for that we need 2 neon atoms, right? Neon nuclei. So we can say M2 can be formed by taking 2 M1. Yes. By taking 2 M1 you can form 1 M2. But we know when we form nuclei like that, for example, when we consider helium nucleus has mass number 4 and atomic number 2, which means it has 2 protons and 2 neutrons. 2 mass of proton plus 2 mass of neutron, supposed to be the mass of helium nucleus, because it has 2 protons and 2 neutrons. We know what is mass of neutron, mass of proton. When we add them together, 2 times mass of proton, 2 times mass of neutron, we are supposed to get mass of helium nucleus. But we know actual mass of helium nucleus is less than 2 times mass of proton plus 2 times mass of neutron. Actual mass of a nucleus will be always less than its total mass of the constituent particles. Correct? That is what we observed in this example. So total mass of the nucleus is always less than the actual mass of the constituent particles. If so, you cannot say M2 is equal to 2M1. We formed M2, we formed one nucleus of calcium by taking 2 neon nuclei. But if you form a nucleus like that, M2 will be less than what? M2 will be less than 2M1. Yes. When we form a nucleus, some mass will be missing. That was called mass defect, right? Here we had a mass defect. Yes, delta M is the mass defect. So this is the correct matching option. So M2 less than 2M1. This is one of the option A, right? M2 less than 2M1 is the correct answer. But look at this, we have one more option, because since it is given both B and C are correct, so let us cross check other options also. If M2 less than 2M1 is correct, this cannot be the answer, of course, right? Because it says the other way around. And M1, what is M1? M1 is mass of neon, correct? Mass of neon. That is M1 less than 10 mass of neutron plus mass of proton. And look at this, M1 is formed by 10 protons and 10 neutrons, right? 10 neutrons. 10 protons and 10 neutrons. So if you consider mass of M1, 10 protons plus 10 neutrons. How do you know 10 protons and 10 neutrons? Its atomic number is 10, atomic number is 10, so that is number of protons, and mass number is 20. Mass number minus atomic number will be the number of neutrons, so they are equal here. So M1 supposed to be less than what? 10 times mass of proton plus 10 times mass of neutron. So M1 should be less than 10 times mass of proton plus mass of neutron. See, unfortunately M1, that option is also correct, right? M1 less than 10 mass of neutron plus mass of proton. See, A and C are correct. So you have to just change this into both A and C, correct? Then D is the correct answer. Yes. Yeah, both A and C should be the correct answer. So M1, M2 less than 2M1, that is a correct statement. Even M1 less than 10 times mass of neutron plus proton, mass of proton is also a correct option. Okay, so that was question number 9. I hope it is clear. Yes, so don't just mark one single answer and keep going. If you have both A and B or both A and C options like that, cross check for the other questions also, other options also. There may be combinations correct like this. Okay, yeah. Question number 9, option D. Yes. 10th one. Binding energy per nucleon is almost constant for many nuclei. It shows that nuclear forces are. Binding energy, we were dealing with binding energy so far. Slowly we are coming to the nuclear force, its influence, stability, that kind of concepts. Okay, we are going to connect them together. Okay, binding energy per nucleon is almost constant for many nuclei. How do you know that? That is the very first question. Okay, then it shows that nuclear forces are. Some properties of nuclear force is given as options. Let's go through that. Charge independent, nuclear force is charge independent, saturated in nature, short range in nature, attractive in nature. Basically all of them are. Yes, many of you are going with C because that is a very popular, very common property that we remember for nuclear forces. It's a very short range force. Nuclear force is it operates between nucleons only if they are very close to each other. But it is charge independent also. That is also a true property. Yes. And attractive in nature. Basically, nuclear force is attractive. Basically, most of the time nuclear force will be attractive. Then these three we are sure about. And what about B? Saturated in nature. Saturation of nuclear force. So I am going to repeat the same question here. Why? How do you know binding energy per nucleon is almost constant for many nuclei? Most of the nuclei, binding energy per nucleon is a constant. How do you know? That is clear from the binding energy per nucleon versus mass number graph. This is one of the important graphs that we have to go for, right, in this chapter. Two graphs we have. One, binding energy per nucleon versus mass number graph, the one which you can see on the board right now. One more graph is coming soon in the coming questions. That is potential energy versus internucleon distance, the one which I listed in the beginning, in the topics. Okay, see, from this one, it is clear that 8 MeV. See, 8 MeV. This is the 8 MeV mark. Binding energy per nucleon. This is binding energy per nucleon in MeV along y-axis. And along x-axis it is mass number. Okay, see, mass number is varying and here binding energy is varying here. And you can see most of the elements, most of them coming from around 25 or 30, from 30 up to 170 mass number. See, the range. Mass number from 30 to 170. Binding energy, average binding energy per nucleon is what? 8 MeV. So that is a wide range of number of nuclei, right, or elements we can see. So for almost all of them have an average binding energy of 8 MeV. That is what the first part of the question says. Binding energy per nucleon is almost a constant for many nuclei. For many nuclei coming in this range, 30 to 170, they have one constant binding energy per nucleon, which is 8 MeV. This is because of one of the property of this particular nuclear force, and which property is that is the question, and the correct answer is option B. Nuclear force is saturated in nature. Okay, if you add more and more nucleons into a nucleus, or if you coming to higher nuclei, see, when in the graph it is clear, when you come more than 170, when you go more than 170, mass number is more than 170, binding energy per nucleon goes below 8 MeV. Even very light elements, less than 30, they also have binding energy per nucleon less than 8 MeV. So binding energy per nucleon is not increasing proportionally with the mass number. It is increasing, almost a constant, then decreasing. And that is because of the saturation property of nuclear force. What do you mean by the saturation property? We know it is a very short range force. Since it is a short range force, when you add nucleons together, like so many nucleons inside a nucleus, it is a very short range force. The force is operating only between 0 FM to 3 FM. This is the range. What is that FM stands for? Fermi, 10 raised to minus 15, right, meters. So that is the range of operation of nuclear forces. So when you add more and more nucleons, this nucleon, the one which I selected, will not have any influence or any attraction, any force with this one, because that nucleon will be far away from it. It will be more than 3 FM. The distance may be more than 3 FM. So even if you add more and more nucleons, nuclear force may not change much. Therefore, binding energy also remains a constant. The nuclear force attains a saturation. Why it attains a saturation? Because of this short range behavior. Since it is a very short range force, even if you add more and more nucleons into the nucleus, or if you go to the higher mass number, the interaction between the nucleons is limited to the neighboring ones. So this nucleon can interact only with the surrounding ones, all these nucleons. It cannot interact with this one because it is far away, more than 3 FM. So it will be saturated. Since nuclear force is saturated, binding energy also will be saturated. So the question now makes sense. Read that once again. The binding energy per nucleon is almost constant for many nuclei because of the saturated nature of nuclear force. Yes, I hope it is clear. Yeah. Yes, all of them are properties. Yes. Yes, Albert. All these 4 options are properties of nuclear force only. Okay. But this behavior, binding energy per nucleon, is going to be almost a constant for many nuclei, not because it is charge independent, not because it is attractive in nature, not because of this. It is because of the saturated nature of the nuclear force. I told you all the 4 are properties. Exactly. Okay, question number 11. Yeah, again a question based on the same graph. This is the nuclear binding energy per nucleon versus mass number graph given, and some elements are marked X, Y, Z and W. Look at this. Binding energy per nucleon versus mass number curve for nuclei is shown in the figure. W, X, Y and Z are 4 nuclei indicated on the curve. You can see in the graph given below, there are 4 nucleons given, right? So 4 elements, 4 nucleus are given. Okay, the process that would release energy is, I told you just before, when will energy be released during a process? Energy will be released, or that energy released is actually gain in binding energy. There should be a gain in binding energy during that process. Binding energy should be gain, it should be more. That means binding energy final should be greater than binding energy initial. That is a condition, right? Then only there will be release of energy. Energy will be released. Correct? Binding energy final should be greater than binding energy initial. Okay, now you're given 4 options, 4 transitions, or like 4 conversions. One element converts to the other. Some of them are fission, some of them are fusion, right? You can given. So in that process, which of them will be an energy release? Which process would release energy is the question. So we have to cross check in which of the process binding energy final is greater than binding energy initial. That is what you have to cross check. Okay, look at the options one by one. See, Y, the first option says Y divides into 2Z. Y divides into 2Z. Okay, look at that. Y is the highest binding energy molecule, nuclei given in all these 4, right? That splits into 2. So what happens? What will be the binding energy in the first case? See, you have to refer this graph throughout in the solution. Okay, so I'll just move on to the next page. So the first one was Y changes to 2Z, and look at this graph. Y has binding energy per nucleon, how much? 8.5. 8.5 into 30. 30 is the mass number. What will be total binding energy? Binding energy initial. Binding energy initial is binding energy of Y. Binding energy of Y minus 2 times binding energy of Z. Correct? So we can calculate that value here. Binding energy of Y is 8.5 into 30. 8.5 into 30. Okay, that is initial. This is the binding energy initial. Now, what is the binding energy final? We have to find out binding energy of Z, because we are going to get 2Z. It is going to be 0. Right? 2 into 0. Look at the graph. See? 2 into 0. Why should we multiply 30 and 8.5? I hope you got it. 30 is the mass number and this is binding energy per nucleon. Look at the graph. 30 is the mass number given and 8.5 is the binding energy per nucleon. Yes, yeah. So binding energy per nucleon into number of nucleons. That is the total binding energy. That is why 8.5 into 30. Anyway, we don't have to spend on this particular option because final binding energy is not greater than initial energy. So A is not an option. Look at the next one. The second option given is W is splitting into X plus Z. W. The element W splits into X plus Z. So when you go to the second option, W splits into X plus Z. What is the initial binding energy? W. Initial binding energy. W has 120 nucleons and 7.5. So we can say 7.5 into 120. That is the initial binding energy. Binding energy initial. And binding energy final is for X and Z. X plus Z. X plus Z. What is X? 90 nucleons, 8, right? So we can say 90 into 8 MeV plus 90 into 8 MeV plus Z is going to be again 0, right? Whenever Z comes, it is easy for us, it is 0. So here we will get the transition, like change in binding energy, and we will check option 3. Option 3, go back to the graph once again. In option 3, W splits into 2Y. W splits into 2Y. We already calculated for Y. Y it is 2 into 8.5 into 30, right? It's actually 60 into 8.5. That is what? The binding energy final. And what about W? W we can calculate from this 120 into 7.5. 120 into 7.5. This is binding energy initial. Binding energy initial, binding energy final. And for the last option, see, you have to cross check the values. Okay, finally you have to tell me in which of them binding energy initial and final is greater than that of initial. The last option is X splits into Y plus Z. X splits into Y and Z. See, we know Z, nothing to contribute. X we already calculated somewhere here. It was 90 into 8, right? That is binding energy initial, and binding energy final is Y plus Z, and Y is a 30 into 8.5. This is binding energy final. Binding energy final. Yes. So out of these 4 options, the condition for energy to be released, we know. Condition for energy to be released, what we have to cross check is in which of the case binding energy final is greater than binding energy initial. And you can cross check those values. We already ruled out this one, right? Option 2 is also not. Check option 3 and 4. In which of them we get binding energy final is greater than binding energy initial. Yes. So here also we get 720, right? So here it is going to be around 250, approximately around 250, right? 30 into 8.5 is going to be that. So fourth is also not an option. So possibly, yes, third option. W splits into 2Y. Yes, exactly. Flip-flop. Yeah. So that is the option C. W splits into 2Y. That is the correct option for this question. So one point I want to remind you here, energy release process. I just considered all those transitions. I just calculated them individually just to get an idea about, in all the cases, binding energy may not be gained, right? If it is a gain in binding energy final should be greater than binding energy initial. Only in those processes, energy will be released. So out of these 4 processes, we calculated binding energy in each process, and we found only in 3 binding energy final is greater than binding energy initial. Okay. And the point you have to remember here, how to calculate binding energy, I explained, and just going through that once again. If you want to find binding energy of Y, binding energy per nucleon is 8.5 and mass total number of nucleons is 30. So binding energy of Y, that is how we calculated this, binding energy of Y is equal to 30 nucleons into 8.5 MeV per nucleon, right? So that will be total binding energy. That is how we found binding energy of all these elements. You are given binding energy per nucleon along y-axis, mass number along x-axis. So we checked what is the binding energy initial and final in all the 4 processes. In this case only, binding energy final found to be greater than binding energy initial. Therefore, definitely there will be an energy release. Yes. Yeah, there will be an energy release in that process. So option C is the correct answer. Yeah. Okay, so I hope it is clear. I spent a lot of time for that because I wanted to explain what exactly happens when binding energy is gained, or what do you mean by energy is released. Yeah. Moving on to the next. Question number 12. Nuclear forces. Binding energy related to nuclear force. Stability I told you, so we are coming to that part now. Nuclear forces exist between, come on, this question is for you. Yes, Hadia. Okay, Abin. Shadi. Samuel. Yes, Allah, Yusuf, Albert, Dhruvil. Yes, guys. Thanks for the responses. Is option D, right? Option D, all of this. It is charge independent. Nuclear force is operating between proton-proton pair, proton-neutron pair, and even neutron-neutron pair, right? There is no discrimination between nucleons, whether it is a proton-proton, neutron-neutron, or neutron-proton combination, irrespective of the nucleons, the property of the nucleons, nuclear force is operating between them. Okay, so option D, question number 12. Moving on to the next. Yeah, let me remind you, this is the second graph you have to remember from the chapter. First one we have done with that, like you know, binding energy per nucleon curve, right? Binding energy per nucleon versus mass number curve. That is one of the important graph. You may be asked to draw the graph and explain or the observations you can make based on the variation of binding energy per nucleon. In the same way, this graph, potential energy of nucleons versus separation between nucleons, internucleon distance, that graph is also very important. We get even 3 mark questions to explain observations you can make or the properties of nuclear forces based on this graph. Okay, not only MCQs, right? So graph gives the variation of potential energy of a pair of nucleons. Yeah, pair of nucleons as a function of their separation. R is a separation. From the graph, it can be concluded that force between nucleons is attractive for a distance. Yes, I got many answers correctly. Between the nucleons, attractive force will be operating when the distance is less than R0. There is a reference point given here, R0, and this is 3FM. We know the graph, right? How to explain the graph. We have taken potential energy along y-axis. So this is the potential energy 0 mark. So below this it will be negative potential energy, above positive potential energy. Potential energy between 2 nucleons, when you increase the distance, I am going to keep 2 nucleons together like close to each other. I am going to increase the distance between them. When I increase the separation R, potential energy is found varying. That variation is given in the graph, right? And we have to remember the nature of the force based on the potential energy. Whenever potential energy is positive, the nature of the force is repulsive, right? Repulsive. This is not new for us. In electrostatics, we learned how to find out potential energy between 2 charges. If you have 2 positive charges, Q1 and Q2, what will be the nature of the force between them? It is repulsive force, right? Repulsive force. And the expression is U is equal to K Q1 Q2 by R, correct? Both of them are positive. Your potential energy will be Q1 is positive, Q2 positive, potential energy will be positive. Look at this. If the potential energy is positive, force between them is repulsive. Now, what happens if both of them are negative? If both charges are negative also, minus Q1 minus Q2 becomes positive again, right? Yes. So again, force will be repulsive. So whenever potential energy between two bodies is positive, or a two-body system is positive, remember, force operating between them is repulsive. Okay? It is repulsive. And when the force is, what is the condition for force to be attractive? Yes. As we know, if potential energy is negative, force is going to be what? Attractive. That also can be explained with the same example because we are familiar with this. That is why I straight went to the electrostatics. Yes, if you have one negative charge, one positive charge, what type of force will be acting between them? Attractive force, mutual attraction. And if you find potential energy of this system, U equals to K Q1 Q2 by R, one of the charge is negative, your potential energy will be negative. So whenever potential energy is negative, remember, force operating between those mass system is attractive. Not only this, do you remember that gravitational part we learned in 11th? In gravitational potential energy, U is equal to minus G m1 m2 by R. There is a permanent minus sign in that particular equation. See, mass cannot be negative, mass m2 cannot be negative, distance is just the magnitude of the distance between the two masses. So none of these terms can be negative. This minus sign will be there permanently because force between two masses, gravitational force, is always attractive. It can never be repulsive. If it is repulsive, potential energy will be positive, but here force is attractive, so it will be permanently negative. Okay, the point I was trying to make, when potential energy is positive, force repulsive. Potential energy negative, force attractive. Correct? Yes. Go back to the that particular graph. We can see potential energy is positive in this range, right? In this range, potential energy is positive. And for this range, potential energy is negative. And whenever potential energy is positive, I told you already, the force will be repulsive. And here force is attractive. Look at the variation. At R0, the potential energy decreases. At R0, it turns to the next part, like negative side. That is how it is varying. So the force becomes attractive if the potential energy is negative. So you are asked to find the range from the graph. Potential energy turns to be negative in this range, greater than R0, up to 3 FM till the end of the graph. So greatest option here is greater than R0. Okay, many of you already answered that question. I was just running through the concept. Hope it is clear. Question number 13, it is option B. Now, next one. Again, a similar question based on the same graph, more conceptual, but you can now answer it very easily. Graph gives the variation of potential energy of pair of nucleons as a function of their separation. Exactly the same description given. From the graph, it can be concluded that if the distance, yes, the conclusion they are given here, if the distance between the nucleon is greater than R0 but less than 3 FM, value of R is greater than R0 but less than 3 FM. What is that? This range, greater than R0 up to 3 FM. This range they are talking about. The nature of the force between the nucleon is, yes, exactly. So this almost the same question asked in another way. So we know potential energy is negative. If potential energy is negative, the force will be attractive. Yes, attractive. That was option B. Correct? Question number 12 and 13 and 14 was based on the graph. Remember, revise that graph properly. Understand the concept. Yes. Question number 15. Binding energy. The binding energy per nucleon for a deuteron and an alpha particle are X1 and X2. X1 and X2 are the binding energy per nucleon for a deuteron and an alpha particle. The energy released in the reaction. Yes. Energy released in the reaction. Can you identify what reaction is this? Which reaction is this? a deuteron, a deuterium is added to one more deuterium, we are ending up with a helium nucleus. So two lighter nuclei fuse together to get a S Dhruvyl. Exactly. So to get a bigger one, right? Yes, Hadia. Okay, Alan. Yes, Albert. Yeah, so X1 and X2 are the binding energy per nucleon given, and we are ended up with a fusion reaction here. Energy released. I told you energy released is binding energy difference, right? Q value, energy released, is equal to binding energy final minus binding energy initial. We did similar questions before, so now it is easy for us. What is binding energy final? Binding energy of the products. We have only one product here, helium nucleus, right? Helium nucleus. What will be binding energy of helium nucleus? Read the question properly. Okay, don't be confused. Whenever it is binding energy per nucleon, remember the given value X1 is not total binding energy of helium. It is binding energy per nucleon of helium. Correct? So binding energy per nucleon of helium is X1. How many nucleons are there in helium nucleus? There are 4 nucleons, right? Yes, there are 4 nucleons. So 4 into X1. 4 into X1. That is the final binding energy. We have 4 nucleons. X1 is the binding energy per nucleon for helium. So 4X1. Minus, what is the initial binding energy? In the same way, remember binding energy per nucleon is given for the other one also, right? For deuterium or deuteron. X2 is the binding energy per nucleon. And we have 2 deuteron added. So we can say 2 in 1. One of them is one deuterium has 2 nucleons inside. So 2 into X1 plus 1 more 2X1. Why? We have 2 deuterons added, right? 2 deuterons, 2 deuterium added. So initially, this is the binding energy of initial binding energy of this part, ending up with the final binding energy. The difference between the two will be the final answer, energy released. So now it is easy. 4X1 minus 2X1 plus 2X1 becomes, sorry, second one is X2, right? So it is 2X2 and this also 2X2. Binding energy per nucleon of deuteron is X2. So this is 4X2. You can take 4 out, 4 into X1 minus X2. Yes. 4 into X1 minus X2 is going to be alpha particle X1 and X2. Okay, sorry. We have taken it the other way around. Nobody noticed also. For neutron it is X1, alpha particle it is X2 respectively. Okay, be careful. So the first one, if you go for alpha particle, it should be X2. For deuteron, it should be X1. Yes, so 2X1 plus 2X1 once again. So we get 4X2. This is 4X1. So X2 minus X1. X2 minus X1 is option B. Yes. Yeah. That was the energy release. See, whether it is fission or fusion, irrespective of the process, energy released is going to be change in binding energy. Binding energy final minus binding energy initial. Okay. So we get questions to calculate Q value. In some question it will be given, what is Q value of reaction? Q value of reaction is nothing but energy released. Okay, energy released in the process. Yes, that is what this Q is given in the reaction. Okay, usually that heat is, energy is coming out in the form of heat. That is why we use Q. Okay. 16. Again, a binding energy per nucleon question. You are given a deuteron, again a deuterium, its binding energy is 1.12. The only thing you have to check whether it is the total binding energy or binding energy per nucleon. In the previous question, we got binding energy per nucleon here. For deuteron is 1.12 MeV, and helium nucleus has a binding energy of nucleon 7.047 MeV per nucleon. Again, both of them are binding energy per nucleon. Then in the fusion reaction, energy released will be, the only difference here, you are given some numerical values. Before it was just X1 and X2 in the previous question. Here you are given some definite values for binding energy per nucleon. So just numerical calculation, nothing else. Okay, exactly the same process. Binding energy final minus binding energy initial is going to be the energy released. So what is the total binding energy final? 4 nucleons into how much? 7.07. See, this is the binding energy per nucleon of helium nucleus. So we can say 4 nucleons are there. Each nucleon has 7.047 binding energy. Okay. Minus binding energy initial, we have 2 neutrons, right? So we can say 2 into 2 nucleons into 1.112 plus 2 into 1.112, right? That is the total binding energy initial. So it is easy to calculate. 4 into 7.047 minus, again this also 4 into, right? 2 plus 2 is going to be 4 into 1.112. Yeah, you can simplify this. 4 into 7.047 minus 1.112 MeV. This will be your final answer. Just subtract 7.047 minus 1.12. That will be somewhat 6 point something. 4 into 6 is going to be 24 approximately. So if you have an option with 24 MeV, that can be the final answer. And that is option C. Yeah, exactly. Yes, Hafiz. Option C is the correct answer. Okay. Yes. So time is up. We are already out of time. So then the points you have to remember when you go through nuclei, right? Make sure you're okay with those 2 graphs properly. That is what the first thing I have to remind you. We get repeating questions from both the graphs, binding energy per nucleon graph and also potential energy versus internucleon distance graph. Okay, those 2 are repeating questions, both conceptual and these kind of numerical questions can be expected, right? Apart from that, like profiling of nucleus, that was an easy topic, right? And nuclear reactions, energy released in a nuclear reaction, that part is also important. We did many examples from that part. All of these concepts are closely related to the binding energy concept. So have a clear picture of binding energy first. What exactly binding energy? What is the role of binding energy? What is the source of binding energy? Everything. Then only we can explain all this process easily. Okay. Yes, I think it's time to wind up. Fake flip-flop. First you have to enter your name, then only I can tell you my name. You're coming with a fake name? Yes, Jane. Yes. Yeah, my name is Sunil and we'll meet with more topics later maybe. Yes, Allah. Thank you. Thank you so much. Thank you all and keep going. Okay. Atoms and nuclei are the 2 chapters we revised. So that was like small chapters comparing to some many other chapters. Topic wise it is very less and some portions are deleted also. Make sure we are not losing any marks from these parts. Simple topics. Okay. Thank you all. Bye-bye.
Brilliant Qatar, your trusted coaching partner for IIT, JEE, NEET, Science and Commerce tuitions with 10 years of excellence in quality training. Brilliant Qatar.